Anything else? Okay. Yeah. Hello everyone. In the previous class, we came to know about electrochemistry, electrochemical cells. What is electrochemistry and electrochemical cell, and how to construct an electrochemical cell or galvanic cell. What is meant by half cell, and what is meant by electrode potential, right? And how to find out standard electrode potential of half cell. About this, we had a discussion or a presentation, right? Now, we will moving on to the next issue. Suppose if you want to find out the potential of the half cell in non-standard conditions. In standard conditions, when the metal rod or metal strip is dipped in 1 molar ionic solution of it, and when we measure the electrode potential values, right, we call it as standard electrode potential. If it is not 1m solution, so how to find out the electrode potential of that? So this is given by Nernst equation. Okay, let us know about the Nernst equation and how to apply the Nernst equation to solve or to get the electrode potential of the different cells at different conditions, right? Right. Right. The Nernst equation. Nernst has proposed an equation and which is useful for finding out electrode potential in unstandard condition. Okay. In thermodynamic standard condition we have seen, and in the standard condition there will be 1m solution, 1 atmosphere for the pressure for the gases if the gases are components. Okay, all liquids and solids are taken in their standard states, thermodynamic states, and temperature is 25 degrees Celsius. These are the conditions when we measure standard electrode potential. Okay, but if it is not the condition, then the Nernst equation can be applied. The simple arrangement to find out the electrode potential values, right? Now coming to this, the value of the cell potential changes if the conditions are non-standard. So what are the non-standard conditions? The Nernst equation describes the electrode potential of non-standard conditions. Suppose if there is a half cell equation, metal in its nth plus oxidation state receives n number of electrons or get reduced to solid metal. Nernst equation tells that electrode potential is equal to E0, standard electrode potential, minus 2.303 RT by NF log of concentration of the one which is in the right hand side, that is metal, divided by concentration of Mn plus. And as you know, for the solid, concentration is taken as unity. Okay, this is the active mass which is taken as unity, and therefore this is 1, and m to the power n plus, m to the power n plus is to be taken in the denominator. This is Nernst equation, right? Okay, now let us try to apply the Nernst equation for this half cell. Okay, if this half cell, if it is to be applied, then E is equal to E0 electrode potential. E0 means standard electrode potential of the cell, standard electrode potential of the cell, it is not high enough, 2.303 RT by NF, where R is the gas constant, T is the temperature in Kelvin scale, N is the number of electrons involved, and F is the Faraday in charges, that is approximately 96,500 coulombs. Right. Log of zinc 2 plus ion by copper 2 plus ion. Now, why this zinc 2 plus ion is to be taken here and copper 2 plus ion here? This is from the equation. Now the cell is represented here. From the cell, you can able to get the cell equation. This is left half cell in which oxidation takes place. Now oxidation takes place means zinc should be converted into zinc 2 plus ion. Zinc is to be converted into zinc plus 2 plus ion. This is oxidation. Right? Copper half cell in which the copper ions give copper metal. Now this is the overall equation. You can write the overall equation from the cell representation, because by knowing the left half cell is oxidation half cell, zinc gives 2 electrons to the copper ion by forming zinc 2 plus, and copper 2 plus ion receives the 2 electron to get reduced itself to copper. Now, in order to apply the Nernst equation, pick up the equation in which the species, ionic species, kept left in the right hand side of the equation to be written in the numerator, and the ionic species in the left hand side is to be written in the denominator. So if it is written, then it is the Nernst equation expression can be given. Now these concentrations are measured before attaining equilibrium. Suppose if equilibrium is attained, then there will be no change of concentration. You know that equilibrium state is defined as such. Equilibrium state is the one in which the concentration won't change. Of course, it is dynamic, but the concentration won't change. This is called reaction quotient and denoted as Q. So Q has got the same expression as equilibrium constant, but measured before attaining equilibrium. Therefore, this is the Nernst equation. But we can modify this, right? We can modify this by taking the respect values, the values of this at 25 degrees Celsius. Suppose we are, normally these experiments are conducted at room temperature. We consider it as 25 degrees Celsius. And therefore, we can substitute these values also. This is 2.303 RT by NF. And we know the value of R, gas constant, 8.314 joule per Kelvin per mole. And the Faraday, 1 Faraday is equal to 96,487 or 96,500 approximately. Okay, joule, coulomb volt. And Q is the reaction quotient, right? Now let us apply these values, and at 25 degrees Celsius, at 25 degrees Celsius, okay, at 25 degrees Celsius, we can modify the value 2.303 RT by F by substituting these values, and what we get is 0.0592. Therefore, instead of writing 2.303, E of the cell is equal to E0 cell minus 2.303 RT by NF, we simply write 0.0592 by N, where N is the number of electrons in the transit. In the zinc copper cell, zinc gives 2 electrons, and the copper 2 plus ion receives 2 electrons. Therefore, the N value is 2, right? Now, let us take the example and numerical and understand it further. Write the Nernst equation for the following cell and find the EMF at 298 Kelvin, that is 25 degrees Celsius, 298 Kelvin. Given that Mg2 plus bar Mg, that is standard electrode potential of magnesium, is being given, standard electrode potential of copper 2 plus ion to copper is being given. And for this cell, we have to find out. Note here, while writing, they will give the information of the concentration in the cell representation. In the cell representation itself, they give the concentration of the species, Mg2 plus ion, 0.001 m. So this can be written as 10 to the power minus 3 m. Okay, and it is 0.0001 m, that is 10 to the power minus 4 m. Molarity. M stands for molarity. Right. Now, let us take the equation. E of the cell is equal to E0 of the cell minus 0.059 by n into log of. So log of, so look at this. So you have to, by knowing the cell representation, you should be able to write the equation. So here magnesium is undergoing oxidation. So magnesium is undergoing oxidation, Mg to Mg2 plus. Mg gives Mg2 plus ion, and the 2 electrons given is taken by copper ion to form copper. So while writing the equilibrium or reaction quotient expression, which species should come to the numerator? One which is at the right hand side of the equation. This will come to the numerator and this come to the denominator, right? Okay. So Mg2 plus in the numerator, Cu2 plus ion in the denominator. So substitution. Now E0 of the cell can be found out. E0 of the cell is found out. Look at this. E0 of the cell is E right minus E left. The right half cell is copper half cell. Okay. E0 of the cell, I will write here. E0 of the cell is given by, if the two half cells are being given, then this is E0 of right half cell, that is Cu2 plus bar Cu, right half cell. In the cell notation, it is the right hand side part, and minus E0 of left half cell, that is Mg2 plus bar Mg. So these values are given. Okay, plus 0.34 minus 2.375. This minus of minus becomes plus, and it will be nearly equal to 2.68, right? Okay, it is being solved here. 0.34 minus of 2.36. This is E left, E right minus E0 right minus E0 left. Now coming to substitute, 0.059 by 2 log of 10 to the power. So in the 10 to the power, if you write, you may understand better, right? 10 to the power 10 to the power minus 4 there, and 10 to the power minus 3 here, right? So okay, it may not be written correctly. So this will be log of 10, right? So 2.7 minus 0.59 into 591 into 2 log 10. Maybe 10 to the power 10 square it will come. Let me just check that. Right. So the concentrations terms. So this is Mg2 plus ion concentration divided by copper 2 plus ion concentration. This is Q, reaction quotient. So if it is written correctly here, then it is Mg2 plus ion concentration is 10 to the power minus 3, and this is 10 to the power minus 4. 10 to the power minus 4. Then the value of this one is 10 itself, because 10 to the power minus 4 will become 10 to the power plus 4, and it becomes 10, right? So it is log of 10. Okay, it is not 2 into. So correct to 5 place of decimal it is being given. And 2.7, so multiply this, log of 10 is 1. Therefore, divided by 2, it should be divided by 2. 0.059 divided by 2, it's not 1, divided by 2, right? So this is 2.67 is the answer. 2.67 is the answer, right? So this is how we can able to find out electrode potential in a non-standard condition by using Nernst equation. Right. Let us see now the relationship between the E0 of the cell, standard electrode potential of the cell, gives free energy change delta Z0, and equilibrium constant K, thermodynamic factors relationship. Okay. For a Nernst equation, we have this Nernst equation for an arbitrary reaction, say A moles of A plus B moles of B, giving rise to C moles of C and D moles of D. For this arbitrary equation, we have the Nernst equation, right? Suppose the cell attains equilibrium, say. This is a cell reaction. By looking at the cell reaction, equilibrium constant expression can be written. Before attaining equilibrium, this is reaction quotient. This is reaction quotient Q value, right? Suppose if it attains equilibrium, there will be no change in the concentration at all. So that will be constant Kc. This becomes a constant when equilibrium is attained. When equilibrium is attained, there is no change of concentration. There will be no movement of electrons also. So E of the cell will become 0. So when E of the cell becomes 0, this E of the cell becomes 0, and this becomes K, then this minus this will be equal to 0, and hence these two are equal. Right? This must be equal to this, right? Because subtraction of these two will become 0 at equilibrium. Therefore, this is the relationship between equilibrium constant and E0 of the cell. Okay, E0 of the cell is equal to 0.0591 by N into log of Kc. Right. Now, the relationship between E0 of the cell and, let us see, the delta Z0 with it. Right. What is delta Z0? Standard gives free energy change. Standard gives free energy change. This gives you the total decrease in the energy of a system. In any system or any process, the total decrease in the energy can be calculated by knowing delta Z0 value. Standard gives free energy change value. For an electrochemical cell, particularly an electrochemical cell, come to the electrochemical cell, decrease in the free energy of the system is nothing but electrical energy produced. Whatever the energy decreased, that much energy is produced. Even in the case of enthalpy change, that was the way it has been explained, right? The energy of the reactant and energy of the product. Energy of the reactant is more than energy of the product. If the reaction happens, the difference between the energy of the reactant and the product, heat content, is given out, exothermic. In the same way, here delta Z0 becomes negative, it is given out. What is being given out? Electrical energy produced. Electrical energy is given out by the system, therefore negative charge, negative sign. So also, this is nothing but, if it is electrical energy produced, then energy, the definition is generalized force into generalized displacement. What is the force? Electromotive force. EMF of the cell itself is the force, and the quantity of electricity that is passed through, quantity of the charges that is passed through itself is what is displaced. So for any energy, so the definition, we can go with the definition, generalized definition. So delta Z0 is equal to minus negative charge because the energy is being given out. NF is the quantity of electrical charges that is being passed through, and E0 of the cell is electromotive force. Okay, force into displacement, right? So again here F is equal to 96,487. We practically take 96,500 for calculations. Okay, and N is the number of electrons. Delta G0 of the cell, Z0 of the cell Standard gives free energy change is negative sign NFE0 of the cell, right? This is the expressions for it. Now we know that delta Z0 is NFE0 of the cell. And first we have again derived that E0 of the cell is equal to 2.303 RT by NF log of K. Or at 25 degree, we might have taken this as 0.059, but you can again make use of it. Now substitute this E0 value here. Substitute E0 value here. Then what we can able to see is delta Z0 is equal to minus NF E0 of the cell is 2.303 RT by NF, 2.303 RT by NF log of K. This we have already derived, right? This expression we have already derived. So NF get cancelled. Therefore, delta Z0 is equal to 2.303 RT log of K minus 2.303 RT log of K. This is the relationship between delta Z0 and equilibrium constant of the reaction. So we have derived three expressions or three relations to remember. One is relationship between E0 of the cell. E0 of the cell is equal to, it is already being given here, or this can be written even this way, 0.059 by N log of QC. Sorry, log of K. It is already attained equilibrium, then only we can write. Okay, this is K. Okay. Then another one is delta Z0 gives free energy change is equal to minus NF E0 of the cell. This we have looked into. Then delta Z0 is equal to minus 2.303 RT log of K. Okay, three expressions we are having, right? These three relationships, the direct questions will come in the examinations. Therefore, remember this without mistake, and then you can able to substitute and get the answer, right? So now we can understand these are the three equations. Okay, it is already once again it can be shown there. So these are the three important relationships. And what are the, now we will get by these things, we will get the conditions. What are the conditions at which the electrode, an electrochemical cell works? What is the condition for E0 of the cell? For a working electrochemical cell, what are the conditions? For a working electrochemical cell, E0 should be positive. E0 value should be positive. If E0 is not positive, then it is not working, it is not an electrochemical cell, it is not working electrochemical cell. That cell reaction pertaining to electrochemical cell doesn't happen. Okay. Now, delta Z0, what should be the delta Z0 for a working electrochemical cell? For a working electrochemical cell or any working process, any process which is to be spontaneous, then it should be negative. Delta Z0 should be negative. Okay. For a working electrochemical cell, E0 should be positive. Delta Z0 should be negative. And what should be the value of Kc? Kc, see here, delta Z0 is equal to log of K. Log is there. If K value is less than 1, okay, if it is 0.1, say 0.1, then what is the log of 0.1? 10 to the power minus 1. Log of 10 to the power minus 1 is minus 1. It becomes a negative into negative, positive. Delta Z0 becomes positive. Therefore, Kc should be greater than 1. So these are the conditions for working electrochemical cell. Okay. So these are the conditions for that. E0 of the cell should be greater than 0. Delta Z0 should be less than, delta Z0 should be less than 0. K should be greater than 1. Okay. Check your understanding with a small question here. Calculate the standard Gibbs free energy change delta reaction. Calculate the standard Gibbs free energy change delta Z0 at 25 degrees Celsius for the following reaction. Right? What is the equation that we have to recall? The equation that we have to use here, that is delta Z0 is equal to minus NF E0 of the cell. Okay, so we must know what are the other requisites. Okay, so we are knowing N because copper 2 plus gains 2 electrons and lead is giving 2 electrons. So N value is 2. And since 25 degrees Celsius has nothing to do with 96,500. F value is 96,500. For E0 of the cell, we need this particular thing, lead ion, electrode potential values. E0, lead 2 plus ion to lead. This value we need. Okay, in the examination, they must be given. It must be given, right? And electrode E0 of copper 2 plus to copper, right? So from given these two values, you can able to find out E0 of the cell in this way. Copper 2 plus ion to copper, electrode potential is 0.337. This value will be given, is given, okay. Lead value, lead is minus 0.126. You can refer the book if you want. And E right minus E left. This is E left. So that the sum is 0.463. 463 is E0 value. Okay. In the examination, these values will be given. Okay, don't worry. Values are given. So while typing, these values are not written. That's the only thing. So my delta Z0 is minus NF E0 of the cell. N is 2. See, it is written along with the units, mole of electron, 2 moles of electron. 96,500 for the calculation, joule per volt, mole per electron. And E0 of the cell is 0.463 volt. Okay. Now, delta Z0 value comes to be minus 89.4 kilojoules, right? So this is 10 to the power 3 joule is 1 kilojoule. Therefore, accordingly, the answer is kept in kilojoule, right? So this is the way we can able to find the answer. Okay. Now write the Nernst equation for the cell reaction in the Daniell cell. How will it be affected when concentration of zinc 2 plus ion is increased? Daniell cell. Okay. So this is the question on Daniell cell, right? Daniell cell is one in which the cell reaction is this. A Daniell cell is one in which we take zinc metal in zinc sulfate solution and copper sulfate solution in which copper is dipped. This particular cell, okay, and salt bridge and so on. This particular cell is called Daniell cell. Remember that this is a Daniell cell. Now, what is the cell equation for the Daniell cell? Zinc, copper 2 plus ion, giving rise to zinc 2 plus ion, this copper. Now, once you know this, you understand now. Try to interpret the question. Now, write the Nernst equation for the Daniell cell and how will it be affected when concentration of the zinc 2 plus ion is increased. For solving this, we need to write the Nernst equation. How the Nernst equation can be written? This is E of the cell is equal to, probably it is there already written. Okay. E of the cell is equal to E of the cell is equal to E0 of the cell minus 0.059 by 2 log of zinc 2 plus ion, because this is a cell equation. Zinc 2 plus ion is on the right hand side. So it should be in the numerator and copper 2 plus ion in the denominator. Okay. Now this equation will help you to tell about the answer. Now, suppose if zinc 2 plus ion is increased, the numerator is increased, this value is increased. Okay. So the total value, this value is increased. So if the total value increased and if it is having a negative charge, larger value you are subtracting from E0. E0 is constant. If we are subtracting larger value, then it is affected. E of the cell is decreased. So if you increase the zinc 2 plus ion concentration, E of the cell value decreases, because from E0 value you are going to subtract the larger amount, right? This is how you have to understand. Okay. E of the cell will decrease when the concentration of zinc ion is increased. Okay. The same way, if copper 2 plus ion concentration is increased, what could be the answer for this? If copper ion is increased, concentration of copper 2 plus ion is increased, then the denominator is increased. If the denominator is increased, the whole thing value is decreased. This is decreased. This becomes smaller, right? If this becomes smaller, this whole quantity becomes smaller. Smaller quantity, if you are subtracting, then this increases. Okay, so it is related in this way. So writing the Nernst equation properly will be of help when such questions are asked. Now, assertions and reasoning question. Current stops flowing when E of the cell is 0. Current stops flowing when E of the cell is 0. Reason, equilibrium of the cell reaction is attained. Reason, equilibrium of the cell reaction is attained. Okay. So all the options. Okay. So answer is being given. So this is both assertion and the reason are true, and the reason is the correct explanation of the assertion, because at equilibrium E of the cell is become 0 and there is no change in the concentration and current stops flowing. So this is how the assertions and reasoning questions, if it is asked, can be told. Right. Another assertion and reasoning question. E0 should have a positive value for the cell to function. A cell to function, E0 should have positive value. Reason, E cathode, E0 cathode, suppose E0 cathode is less than E0 anode for a working cell. Is it so? So E0 should be a positive value. This is the right thing, absolutely right. Okay, this discussed. But is it so? So recall this, E0 of the cell is equal to E0 cathode minus E0 anode. E0 right minus E0 left. E0 right is cathode, E0 left is anode, left half cell is oxidation negative. Okay, anode. So this, if this is smaller, then it will be negative. E0 of the cell become negative, therefore it cannot be a smaller one, rather than it should be so. Then reason is a wrong statement. So assertion is true, but reason is false. Okay, so this is the explanation, right? Okay, these are the important things to be known in the Nernst equation. And coming to electrolytical cell. Okay, so when two copper electrodes are taken, dipped in a copper sulfate solution, okay, both are collected to a DC current, right? When the power supply is turned on, it will give some reactions that goes on. Oxidation occurs at the end, which is connected to the positive leg of the power supply. The reduction
junction half reaction at the cathode has copper 2 ions gaining 2 electrons to form metallic copper. At the anode, copper metal undergoes oxidation by losing 2 electrons to form copper 2 ions.
Okay. Now, what is electrolytical cell? Another part of it, electrolytical cell. So, electrolytic cell is an arrangement in which only one electrolytic solution is being taken and 2 electrodes are dipped into it, and these 2 electrodes are connected to a DC current, direct current. So, electrolytical cell is an arrangement in which the electrical energy is changed into chemical energy. By the passage of electrical current, there will be some change in the chemicals, which is present there. Electrolyte is going to change, or electrodes are going to change. And let us know more about electrolytical cell. Suppose if you have taken copper sulfate solution and dipped the copper electrodes and passed the electrical current there, what we find is the copper 2 plus ion present in the ionic solution takes the electron from the external circuit where there is the negative end of the battery is connected. It takes the electron and copper is deposited. So this electrode becomes thicker and thicker after the passage of current. But whereas the other electrode, which is connected to the positive terminal, loses electron, it sends electron or loses electron and forms copper ion. It gets corroded. Every copper metal atom will become an ion, right? So this is a chemical change. This is the chemical change which we see. Okay. So electrolysis is a process in which electrical energy is used to drive a non-spontaneous chemical reaction. Another important word, non-spontaneous chemical reaction. So otherwise the reaction is not going to happen. Such kind of reactions are going to happen when electricity is passed through. Okay. So compare that differences between galvanic cell and electrolytical cell. Okay. So the very important thing to remember is anode is negative charge in electrochemical cell, lone. So as I told you, the lone can be applied only for electrochemical cell. Okay. So the left half cell, anode and negative, anode is negative. But here when it comes, anode is positive, cathode is negative. So one thing that you can remember very easily, in order to avoid this kind of confusion, always cations move towards cathode. So cations present in an electrolyte, wherever they are moving, that electrode is cathode. So you can remember very easily. I tell you how. Suppose if it is in an electrochemical cell, the copper ions here are going to deposit it here, then this is a cathode. Then that is cathode, right? So left half cell is anode, you know that this is cathode. And here cations are moving towards cathode only. The cathode, only cations are moving and getting deposited, right? Okay, this is the one thing. And another way of remembering is anode always oxidation takes place. And anode is a place where oxidation takes place, losing of electrons takes place. So anode here, zinc loses its electron and sends electron to the external circuit in electrochemical cell. So anode is the place where oxidation takes place. And here the anode, this is the anode, wherein copper is converted into copper ions. Copper is converted into copper ions, means it loses its electron, right? So these are the two things that you can remember. So polarity is next to that to be remembered. What is thing to be remembered first is, it is the anode where oxidation takes place. Anode is the place. Okay. So anode oxidation, the lone, these two holds good. O and N holds good for both the both the cells, right? Okay, but the polarity only is, the polarity is changing, right? Because cations move towards cathode. Okay, this is what you can learn from it. Spontaneous reactions, and this is a spontaneous reaction. This is a redox reaction. Spontaneous can occur, okay, directly also, but it is indirectly done in the electrochemical cell, but it is not a spontaneous process. Okay, E of the cell is positive here, it is E of the cell is negative here, E of the cell is negative, and Gibbs free energy change is negative. If it is spontaneous, then it should be negative, and delta G is positive here, and these are the differences between these two. Now, the products of electrolysis is again a important thing, and here also the electrode potential values come to the picture. Electrode potential values are quite helpful in predicting what could be the product. Okay, if the electrolyte, if there are more than one cation, which could be the one which reaches the cathode or anode. Okay, so this is a particularly the electrode potential values will come to the play. Let us see how it is to be done. Okay, so the product of electrolysis depends upon the nature of material and the type of electrode. Okay, so we use inert electrodes. Platinum is considered to be inert electrode. It only gives a surface area for undergoing either oxidation or reduction, right? The product of electrolysis depends upon the different oxidizing and reducing species present there in the electrolytical solution and their standard electrode potential. Okay, it's standard electrode potential. Now let us see. Let us take an example. So in this example, molten potassium chloride is taken. Molten potassium chloride is taken here. In this is an electrolytic cell. In this electrolytic cell, molten KCl, one electrolyte is taken. What is meant by molten KCl? KCl is a solid. At high temperature, it is melted. Okay, it is in the liquid form. Okay, in the liquid form, it is having K plus and C plus ion. These ions can move only when it is in the molten state. When it is in solid state, even though there are ions, they can't able to move. They have got a fixed place. They are molten KCl. Okay. Molten potassium chloride is taken. So the two electrodes to the DC current generator source of DC. So this is positive charge. This is a negative. So what do you expect? So there is K plus ion. K plus ion. So K plus ion should go to K plus ion, negatively charged species. It should go here. This is cathode. Cation move towards cathode. Easy to remember. The anion Cl minus will go here. Cl minus ion. This Cl minus ion go and forms a chlorine atom initially, primary change. Then each chlorine atom at the beneath of another, it combines to form chlorine gas. Therefore, there will be evolution of chlorine gas. So, what are the product of electrolysis of molten KCl? It is simple. Potassium ion gives potassium. Molten potassium will be surrounded here, right? So, potassium and Cl2. Chlorine gas will go out at anode. Okay. Chlorine gas will be produced at anode. So, this can be easily predicted. Okay. Now, coming to liquid potassium produced at one electrode and chlorine gas is produced. Okay. So these are the things that I have told you. Now, electrolysis of aqueous potassium sulfate. Now we have changed. One is that potassium sulfate. This is not potassium chloride, potassium sulfate. And another important word is aqueous. Aqueous potassium sulfate. So, aqueous potassium sulfate means it is dissolved in water, right? So, when it is dissolved, these ions are separated. Two K plus ions, sulfate ions are separated. That is one thing. And another thing is that water also is containing H plus ion and OH minus ion. Okay, H plus ion and OH minus ion, because water also undergoes self-ionization. Okay, so even though it is covalent, it produces okay, at 25 degrees Celsius, 10 to the power minus 7 moles, okay, of that hydrogen ion will be there, 10 to the power minus 7, right? Now, suppose if this electrolyte is being taken, aqueous K2SO4 is being taken. So what are the possibilities? The K plus ion and hydrogen ion, K plus ion and hydrogen ion, the two cations are there. They want to reach the cathode. Okay, there is a competition now. Potassium ion and hydrogen ion present in the electrolyte wants to reach the electrode, and it wants to gain an electron and become hydrogen gas. 2H plus ion gains 2 electrons to give hydrogen gas, and K plus ion wants to have 1 electron to become potassium. In this competition, who is going to win? This can be known by electrode potential values. You know that reduction of a strong metal is a negative value, but this is 0. Electrode potential of hydrogen is 0. So which is more than? One is negative, another is 0. 0 is more. Therefore, hydrogen get evolved here. Hydrogen gas is evolved at cathode. Hydrogen gas is evolved at cathode. Now, in case of anode, oxidation should take place. So one is OH minus ion and another is sulfate ion. Sulfate ion, nearly it won't get oxidized, and there is only one option is OH minus ion. When OH minus ion undergo oxidation, oxygen gas which is being formed. OH minus ion undergo oxidation to give O2 gas. Remember this, OH minus ion gives O2. OH minus ion, okay, when it get oxidized, this gives H plus ion and O2 and some electrons. This is the half cell reaction. You can say half cell reaction. So O2, therefore 2 OH minus ion, 2 H plus ion, 4 electrons. This balances the whole process. So this gives O2. And also you can observe that because of the H plus ion, the area wherein you can do the litmus test and see that blue litmus is converted into red, right? So this is also can be understood, right? So aqueous potassium sulfate is not having color. Only to show an electrolyte the color is being made, but it is colorless. And you can see the litmus test. This must change also. H2O giving rise to, okay, you can write OH minus ion gives O2. That is also one way of writing. Another way of writing is H2O, okay. Here the H plus ion present in the H2O gives H2. And here, okay, here OH minus ion present in water gives O2. This is another way. Water get reduced. Water get oxidized. Okay, instead of H plus ion get reduced, we say water gets reduced because H plus ion is from water. Therefore, this is the way that B is being given, right? Right. So, in this electrolysis, hydrogen gas is produced at one electrode, and gaseous oxygen is produced at another electrode, and the solution become acidic near this electrode, and these are experimentally can be seen, right? That is the proof of what the product is, right? Now, commercial application of electrolytical cell. What is the commercial application of electrolytical cell is for electroplating and electrolytic refining. So this electrolytical refining of electrolytical refining of copper is being done by using this electrical current, and the impure copper can be almost 100%. To the extent of 100%, we can get the pure copper. Okay, when the metal is extracted, it will be about 96 to 97% pure. It will be consisting of other metallic impurities. From 97% metal to 100% metal, copper can be got by electrolytical refining. Okay. Okay, for that, what is to be done? As I told you, this is the first one that I talked about was the electrolytical refining only. Okay,
When the
okay, okay. Now, the another thing is that amount of substances produced at the electrode. Amount of the substance produced at the electrode. Okay, what is being produced? We talked about. So that depends upon the electrode potential values and also nature of the electrodes, right? Now, how much is produced is determined by Faraday's law. Faraday's law, there are two laws. The first law says the amount of the chemical reaction which occurs at any electrode during the electrolysis by the current is proportional to the quantity of electricity passed through it. Okay. Suppose there is a cathode and copper is get deposited, say 10 grams of copper is deposited. Okay. And if you want to produce 20 grams of copper to get deposited, more electricity that you have to pass. That is only the simple way of understanding it, right? The amount of substance deposited in an electrode is directly proportional to the quantity of charges that is being passed, quantity of the charge being passed. Okay. Now, mathematically, this is written in this way. The mass of the substance deposited is directly proportional to the quantity of charges passing through it. M is directly proportional to Q. Quantity of charges, how do you measure quantity of charges? This quantity of charges is the amount of current passed through in amperes and the time in seconds. So, mass deposited in an electrode is directly proportional to the current passed in amperes, the I in ampere, and how much time it is taken for passing. Okay, it depends upon that. So when the proportionality sign is to be converted in the form of an equation, there is a proportionality constant, Z I into T. So this Z is called electrochemical equivalent. Here, proportionality constant has got again, okay, in the same way, the proportionality constant will be having name. And how do you define that? The Z electrochemical equivalent is the mass deposited when I is equal to 1 and the T is equal to 1. Okay. So this is the simple definition you can coin, right? Electrochemical equivalent is the amount of substance, mass of the substance deposited when 1 ampere of current is passed through 1 second, right? So this is electrochemical equivalent. And this is the mathematical expression from the Faraday's first law of electrolysis, right? Okay. Right. So this is what I told you just now. M is equal to ZIT. Right. Okay. Check the understanding and take up some of the few of the questions of that kind. How much charge is required for the following reduction? 1 mole of, this is Al3 plus, Al3 plus 2Al. How much charge is required for the reduction of this? For solving such questions, what is the equation that to be written is, for the first question, what is the equation to be written is Al3 plus aluminium 3 plus ion is to be converted into aluminium solid. Say, for this, you need 3 electrons. Because aluminium 3 plus means an atom having 3 electron less. Al3 plus is the 3 plus charge is got by, because it has lost 3 electron. Again, if you are giving 3 electrons, it becomes an atom. Right. 3 moles, if 1 mole of Al3 plus need 3 moles of electron. If there is 1 atom of aluminium ion, if there is 1 ion of aluminium Al3 plus, it needs 3 electrons. If there are 1 mole of aluminium ions, that is 6.022 10 to the power 23, that number of aluminium ions, then 3 moles of electrons are needed. Right? 3 moles of electrons. Okay. So 3 moles of electron. So 1 Faraday is nothing but the charge carried by 1 mole of electrons. So 1 mole of electrons carry approximately 96,500 coulombs of charges. Okay. So 1 Faraday is 96,500. Now you can understand, if Al3 plus to Al, if you want to do, 3 moles are necessary. Therefore, either 3 Faraday of charges required or 3 into 96,500 coulombs of charges required. Right? In the similarly, copper 2 plus ion and
Answer
another
2.
thing. Okay. Answer?
2, sir. Second one. And third one,
Okay.
5.
It is not the optional one. So all the 3, it is a descriptive one. All the 3 we have to find out. Copper 2 plus ion to copper.
Farad, sir. 2 farad and 5 farad.
Okay. 2 Faraday and 5 Faraday. Okay. I don't know how you have calculated about this. Let me just talk about that. Copper 2 plus ion to copper is 2 Faraday. We can able to understand. Okay. So the answer is like this, but method, let you know. In the third case, this is, okay, in the third case, it is MnO4 minus ion to Mn2 plus. Okay. So what you have to remember here is, what is the oxidation state of manganese in MnO4 minus? Oxidation state of manganese is, suppose if it is X and oxygen is -2 always. Okay. X minus 2 into 4. 4 oxygen atoms are there. 8 is equal to -1. X minus 8, total charge together should be -1. So X is equal to -1 plus 8, that is 7. X is equal to 7. Oxidation state of manganese is 7. Plus 7 is converted into +2. That means 5 moles of electrons are needed. You are right. You told the answer. You are right. And 5 moles of electrons needed means 5 Faraday of charges, or 5 into 96,500. And by doing that, we are going to get this answer. Right? Now, how much electricity in terms of Faraday is required to produce 20 grams of calcium from molten calcium chloride? So it is a textbook question. How much electricity in terms of Faraday is required? So calcium chloride, whenever it is given,
Half farad.
okay, Ca2 plus, okay, let us see. Okay, let's verify. Calcium chloride is having Ca2 plus ion. Always take the oxidation state of that. Ca2 plus ion. To convert this into Ca, calcium, it needs 2 electrons. Right? It needs 2 Faraday of charges, or 2 Faraday of charges will deposit 1 mole of calcium. 2 Faraday of charges will deposit 1 mole of calcium. 1 mole of calcium in mass is 40 grams. This is the atomic mass expressed in grams. Okay, there is a molar mass, 40 grams. 2 Faraday required for 40 grams. 2 Faraday is required to get 40 grams. The question is, you want to get 20 grams of calcium. How much Faraday of electricity is needed? Now it is simple. It is 1 Faraday. 2 Faraday is required to make 40 grams of calcium deposited, calcium evolved. Therefore, 1 Faraday is required for 20 grams, right? Not half, it is 20, it is 1. Now, according to the equation, okay, this is the way it is given, solved also. Okay, produced 40 grams of 2 Faraday. Therefore, it is 1 Faraday. Just now I have told about it. Okay. Now, exemplar question, more than one answer correct type. More than one unanswered correct type. What will happen during the electrolysis of aqueous solution of copper sulfate by using platinum electrode? Okay. It is more than one answer may be correct. Okay. What will happen during the electrolysis of aqueous solution of copper sulfate? Here you have taken aqueous solution of copper sulfate. Okay. Okay. And the electrodes are being given by using platinum electrodes. These are inert electrodes. Platinum electrodes, right? This is negative, this is positive. Okay. Aqueous copper sulfate. Now copper will be deposited at cathode. So this is negatively charged. Cations will come cathode. This is anode. Okay. Cations move towards cathode. Therefore, this should be negatively charged. This is how you can recall and make it easily. Now, so this contains copper ions and hydrogen ions. Nice. Okay. Now, copper will be deposited at cathode. Is it so? Whether copper is deposited or hydrogen gas is being evolved. How will you find out? So, for this, what is come to the way is Cu2 plus ion plus 2 electron giving rise to Cu. Hydrogen ion, okay, taking 2 electrons, 2 hydrogen ion taking 2 electrons to give hydrogen, which has got greater reduction potential. So this reduction potential, if you remember, this is 0.36 or 34. And here it is, E0 is 0. For hydrogen is 0. Reduction potential of copper is 0.34. Then this is more, therefore copper should be deposited. This is right. Copper is deposited at cathode is right. Cation should go to the cathode, therefore it should deposit at cathode. That is right. Copper deposit at anode is not the right answer. Copper will not deposit at anode. Oxygen will be released at the anode. Okay, oxygen will be released. Right. So for the oxygen, the anion should go to anode. Which are the anions? One is sulfate ion and the rest is OH minus ion from water. Wherever sulfate ion is there, it won't go for reaction. It is stable. It is stable by the resonance. OH minus ion will be giving O2. Therefore, oxygen gas is released at anode is correct thing. Copper will dissolve at anode is not the right thing. So 1 and 3. 1 and 3 are the correct options, right? Is the exemplar questions. Please see that exemplar questions. So which are challenging are also there, right? Now coming to the another part of electrochemistry, that is conductivity cell. How this conduction occurs? Okay, how this conduction occurs? We know that in metals there are free electrons.
Yes, sir. Yes, sir.
The electrons which are loosely connected are present, right? So these electrons are responsible for conduction of electrical current. They are mobile, they are moving. So the metallic bonding is explained in this way. Metal is set of kernels and free moving electrons. It is an interaction between set of kernels, positively charged nucleus and some set of electrons together, kernels and mobile electrons. So these electrons are responsible for conduction in the case of metals. But what is responsible in electrolytes? They are ions, right? And how to measure the conductivity of these ions and also how much they contribute, whether each ion contribute to the same extent, at what conditions? These are all interesting things to know in this particular unit, right? Now just compare the conductivity values. So there are conductor sodium, copper, silver, gold, iron, graphite. So this is 10 to the power 3 is the order. 10 to the power 3 is the order. Okay. So S per meter is the unit of it. Okay. Glass and Teflon, 10 to the power minus 16, 10 to the power minus 18 is the order. It's conductivity value. Okay. Pure water is 10 to the power minus 5, 3.5 into 10 to the power minus 5 conductivity value. It is all the order, okay, nearly 1 or 10, okay, or less than 1. Okay. This is 0.1 mHCl is 3.91 and all are less than 1. Okay. So metals are very good conductors. Conductivity value is more. But in case of ionic solutions, that is less. Ions do conduct, but meagerly, right? But they are more than insulators, okay, or semiconductors, right? They are semiconducting device, semiconductors like copper oxide, silicon. In that comparison, okay, it is more. Okay. Now, how the metallic conductance and electronic conductance takes place? Let us see this video.
Metallic conductance or electronic conductance is the electrical conductance through metals. As the name indicates.
Okay. So metallic conductance, the responsible one is this electrons, right? So this is in pure water. Also there is conductivity, it is there, right? Okay. Usually this is the schematic diagram of a conductivity cell. Conductivity cell. Okay. So a cell, this cell consisting of a place to accommodate an electrolyte of which conductivity value is to be seen, and this consisting of two metallic electrodes, platinum electrodes, and these electrodes are connected to the AC current, alternate current. So the polarity should change. Otherwise, if it is a DC current, then it will be an electrolytic cell. It will be electrolytic cell, therefore it is AC current we have to apply. So this is the arrangement to measure conductivity of that. So conductivity depends upon the nature of the electrolyte, size of the resulting ions. The size of the ions also responsible. Solvation of ions. Solvation of ion means each ion is surrounded by water. This is solvation. H2O, right? This H2O surrounds every ion. This is called solvation. Concentration of electrolyte and temperature. Concentration of the electrolyte also responsible. Okay, let us see all those things. Okay, electrical, always it is from the resistance we will go. We won't measure conductance, we will measure resistance, right? Even in the metallic conductor that we have done so. Now, suppose if there is a metallic wire, okay, this resistance is directly proportional to length of the wire. You know that it is length of the wire. If the length of the wire is more, the more will be the resistance. And it is inversely proportional to area of cross section. Suppose if it is a wire of this kind, say, so here is cross sectional area. If cross sectional area is more is the conduction. The more is the resistance. Okay, less is the resistance. That means area of cross section is inversely proportional. Inversely proportional. Length is directly proportional. This is about the resistance we have. So we take the reciprocal way we are going to define conductance and conductivity. Now this is resistance. Resistance, if you make equation, then there will be a proportionality constant. That proportionality constant is resistivity. Okay, so this is resistivity. Now take the reverse way. 1 by R is equal to 1 by rho and L by A by L. Okay, A by L. 1 by R is reciprocal of conductance. Reciprocal of resistance is conductance. This is resistivity. Resistivity is 1 by resistivity is conductivity. And A by L is there. For finally, what we can write is, okay, 1 by rho, that is conductivity, is equal to, okay, I have taken 1 by rho, okay. This is conductivity is equal to, okay. So A by L you transfer here. So 1 by R is conductance. Conductivity is equal to conductance. Conductivity is equal to conductance. So if you bring here, this will be L by A. L by A is nothing but cell constant. Cell constant. So it is length between the electrode L and area of cross section of the electrode itself is taken as A. So you know the previous one. So area of cross section of the electrode and the length between them. Okay. So there is L by A, and for a constructed electrochemical cell, it has got a constant value, and it will be pasted on the such kind of cells. Cell constant is equal to so, because it is measured and kept. Now, So this is the way that we are using it, right? Okay. So conductivity is equal to conductance into cell constant. So this is the key thing that we have to use. Okay. SI unit of conductance is Siemens, yes, and S is per ohm. You know that. Okay. Accordingly, you can able to give the different units of that. Now, there is another one that we are interested in chemistry is what if 1 mole of an electrolyte is taken in the solution, how much it is going to conduct. So we want to measure the conductance of 1 mole of an electrolyte. Okay, whatever may be the amount of water taken, whatever may be the dilution of it, but we want exactly 1 mole of each electrolyte. Suppose if it is sodium chloride, 1 mole of sodium chloride, how much it conducts at various concentrations, say. So that is called molar conductivity. So the molar conductivity is the molar conductivity of a solution at a given concentration is the conductance of volume V of a solution containing 1 mole of electrolyte. 1 mole of electrolyte kept between the two electrodes with the cross-sectional area of A and distance of unit length. Okay. Suppose if you think that there is a vessel like this. Okay. So this is one electrode. Okay. And this is another electrode. And both of these are here insulated, right? Insulated in the sense this side and this side won't touch, right? So this diameter is 1 meter or 1 meter, say. So that is of unit length. The distance between the electrode is the diameter itself, right? Unit length. And you are taking the whole of the solution. If you want to measure, if you have kept 1 mole of sodium chloride in 2 liters of water, 2 liters of water, whole 2 liters should be kept between the electrodes and measurement is to be done. Okay, this is what the meaning is. So molar conductivity is conductance due to 1 mole of an electrolyte. This is importantly to be written. Conductance due to 1 mole of an electrolyte, kept between the electrodes, so as to kept between the electrodes which are 1 centimeter apart or 1 meter apart, unit length apart, and the whole of the solutions are between them. Whole of the solution should be between them. Then whatever the measurement that we get, that is molar conductivity, right? So molar conductivity is related to the conductivity. Conductivity is denoted as kappa, K. Looks like K, it's kappa. Lambda m is equal to kappa into 1000 by molarity. So molarity will be moles per liter. And in order to convert this into centimeter, we need to multiply here 1000 centimeter cube by liter. And kappa is measured in S per centimeter. S per centimeter. If all these units are being taken in this way, then unit of lambda m is Siemens centimeter square per mole. Yes, centimeter square per mole is the unit of molar conductivity. Okay, so this cancellation, all these things can be made, right? Okay, so this liter get cancelled, right? Centimeter minus 1 centimeter cube, therefore it is centimeter square. Mole is here, it becomes per mole. Okay, in this way the unit is simplified. Okay. Okay, fine. So how this molar conductivity is related to dilution or dilution, whenever you are going doing dilution, what will be the change in the conductivity value? For a strong electrolyte, what we observe is when you plot molar conductivity versus concentration, when the concentration is increased here, when concentration increases, molar conductivity decreases, surprisingly. molar conductivity decreases. Or on dilution, if you move like this, it is dilution. On dilution, molar conductivity increases a bit. What could be the reason for this? For the strong electrolytes, KCl, when you put whatever the amount of KCl you put in water, it will get separated into ions. Okay. So there is no degree of ionization is not a matter because it is almost undergoing ionization. It is an ionic compound. When you put it in water, immediately it gets separated. Ions get separated. Right. But when you go on diluting it, there is more degree of freedom or the mobility of the ion increases. So on dilution, the ions are free to move, therefore the molar conductivity increases. Okay. So remember, one important thing is molar conductivity increases with increase in dilution, but more conductivity decreases on increasing dilution. Okay. Conductivity is like this. Okay, I'll draw here. Say this is an electrode and this is another electrode. Okay. Conductivity is conductance due to all ions kept between the electrodes which are 1 centimeter apart, and the area of cross section is 1 centimeter square. That is the definition of conductivity. And if the number of ions here increases, concentration increases, therefore conductivity value also increases. That in the case of kappa. Kappa increases with increase in concentration, but molar conductivity lambda m decreases on increasing concentration, right? This is the important thing to be known. Now, suppose if it is a weak electrolyte, more surprisingly, for a weak electrolyte, if you go on diluting it, it increases very fast. Okay. So for the example of acetic acid, okay. So the molar conductivity increases when you are going on diluting it. 0.3 to 0.1, it increased. 0.1 to 0, it is steeply increased. So it may be because of the degree of ionization. This process of ionization needs more and more water. If more and more water is present, then the number of ions are increased. If the more the number of ions, naturally the conductivity value increases. Okay. The undissociated acetic acid get dissociated on dilution. Therefore, it increases steeply on dilution. Okay. So the reasons are different for the strong electrolyte and the weak electrolyte. For the strong electrolyte, it is the mobility of the ions increases on dilution. But for the weak electrolyte, it increases sharply on dilution because of degree of ionization increases. Okay. So another thing that we are observing in this, whenever the case drawn and extrapolate, one can do maximum conductivity, right? So this is called lambda m0. Okay. So molar conductivity at infinite dilution. Theoretically, it is possible, but practically it is not possible to do. 1 mole of electrolyte, you have to put it in sea of water. Okay. So infinitely diluted solution. But you can extrapolate the graph and you can find out the value for the strong electrolyte because it is a straight line. It is a straight line because it is following, okay, d by Haeckel-Onsager equation. D by Haeckel-Onsager equation, lambda is equal to lambda m0 minus k root c, which is of the type y is equal to mx plus c. Okay. Therefore, we are taking root c here. We are taking root c in the plot, right? So this is a straight line. And since it is a straight line, we can extrapolate. But in the case of weak electrolyte, we cannot extrapolate because it is a curve. We don't know where it goes and where it touches, right? Therefore, this lambda m0 for the weak electrolyte, we cannot follow. We cannot find out. Therefore, we have another law which helps in finding out lambda m0 for the weak electrolytes. So for the weak electrolytes, okay, it states that the limiting molar conductivity of an electrolyte is the sum of individual concentration of anions and cations in the electrolyte. Whenever it is infinitely diluted, okay, two solutions I will take, KCl and one is KCl, another is okay, KBr, okay, two salts, and it is kept in infinite dilution. So there will be no relationship between K plus and Cl minus and K plus and Br minus. K is an individual thing. It contributes whether it is same amount to the conductivity, whether it is in KCl or KBr. Therefore, at infinite dilution, the lambda m0 of KCl can be written as sum of the ionic conductivity of K plus ion and ionic conductivity of Cl minus ion. We can write an expression like this. This is from Kohlrausch's law. Okay, if there is an ion, that is individual contribution towards the conductivity, right? So if it is molar conductivity of BaCl2, then how will you write? Lambda m0 for BaCl2, you can write ionic conductivity at infinite solution of Ba2 plus ion plus 2 into ionic conductivity of Cl minus ion, because there will be two Cl minus ions. Okay, so it is an algebraic sum of contributions of anion and cation. So this is the Kohlrausch's law, right? Okay, so that NaCl can be written as Na, and I already written. Okay, so this is Friedrich Kohlrausch who has proposed this. Okay, AyBz, if it is a ionic compound, then Y number of A ion will be there and Z number of B ion will be there, and it is an individual contribution, and this is a general way of writing. Okay, so application of Kohlrausch's law. This law may be used to determine the limiting molar conductivity, degree of dissociation, alpha, and dissociation constant. All these things are practically done by using this, right? So alpha, degree of dissociation, is nothing but molar conductivity at that concentration divided by molar conductivity at infinite dilution. So this is always less than this. This is always more. This is the highest value of conductivity. Therefore, this is always a fraction less than 1 that can match with lambda. For any electrolyte, if you want to find out the alpha value, degree of dissociation, you have to do the conductivity experiment and you can find the alpha value. Okay, alpha is related to dissociation constant, C alpha square by 1 minus alpha. You know this. Therefore, this is the equation that we can use. Equilibrium constant value also you can able to find out by knowing the alpha value. Okay, check your understanding. The conductivity of 0.2 m solution of KCl at 298 Kelvin is this. Calculate the molar conductivity. Calculate the molar conductivity. So molar conductivity is related to conductivity, or kappa. Kappa into 1000 divided by molarity. This is the relationship. Try to recall and then substitute. Okay, K value is being given. This is conductivity value. This is concentration 0.2 m. This is concentration. These two values are given. Therefore, it is easy to do that. Okay. So kappa into 1000 by C. Kappa value into 1000 by 0.2. Therefore, it is 124 S centimeter square per mole. The conductivity of metals decreases while that of the electrolytes increases. Increases with increase in temperature. Why? Temperature factor. For the metals, metal increase of temperature decreases its conductivity. So in metal, what happens is kernels and moving electrons are there. When the temperature is less, kernels are sitting in a place. Okay, they will be in the same place. But when the temperature is increased, the kernel starts vibrating. Okay, they start vibrating. It will be an obstacle for the free movement of electrons, because of which conductivity decreases. Okay, therefore the conductivity decreases in this case. But whereas temperature is increased, the mobility of the ions increases. Therefore, in ionic solutions, the conductivity increases. Okay, with the increase in temperatures, kinetic energy of the metal cation increases and the obstructs the free flow of electrons. Okay, this is what being told here. Right. Exemplar question, one answer correct type. One answer correct type. Come on. Which of the following statements about the solution of electrolyte is correct? Is not correct? Electrolytes, solutions of electrolyte. Conductivity of solution depends upon size of ions. Conductivity depends upon viscosity of solution. Conductivity does not depend upon solvation of ions present in the solution. Conductivity of solution increases with temperature. Okay, so it depends upon the solvation, right? Does not depend upon is not the correct. Okay, is not correct is the answer. Therefore, this is 3. Conductivity does not depend is being given. For solvation, it depends. Therefore, it is the wrong thing. Exemplar, more than one answer correct type. Conductivity of an electrolytic solution depends on. Conductivity of an electrolytical solution depends on nature of electrolyte, concentration of the electrolyte, power of AC source, distance between the electrodes. Does the distance between electrodes and power of AC affect? So 1 and 2 are the one which is power of AC source or distance between electrode is not the thing, right? Right. Okay. So we talk about the various types of cells tomorrow, because the time is up now. There are commercial cells, and how they are getting, how it is constructed, and what is the cell reaction, how to write the cell reaction. Okay, to remember, is there any easy way to remember the writing of chemical equations of these cells? Okay, and objective type questions of the electrochemistry we will do in the morning session, and then we go for D and F block elements. Okay, D and F block elements. Okay, is there anything? Okay, right. So I have put a message there telling you that if you are switching on the phone, then it will be an interruption for the YouTube viewers. Okay, so therefore I request you to give the message by joining Zoom link. You can ask for the Zoom link, and you can put the message, and whatever that you are seeing, I cannot able to see there, right? But the viewers are seeing that. Therefore, please see that it is, you put the messages, right? Okay, thank you. See you. Okay.
I think everyone that's in YouTube only, sir.
Okay.
So in the entry. So after leaving the meeting.
Yeah.
Go to